عليكم السلام.
عليكم السلام.
عليكم السلام.
السلام يا شباب. Can you hear me?
Yes.
Yes, we can.
Yes.
Abdul Rahman, can you hear me?
Yeah.
Can you say
Yes,
with the
we can.
chat because I cannot hear you.
There is noise in your microphone.
السلام عليكم شباب.
عليكم السلام ورحمة الله.
عليكم
Can you hear
السلام.
me?
Yes.
Can anyone answer what's happening? Okay, so you can hear me, but I cannot hear you. Unfortunately for this. طيب, I'll continue now, and if anything, then talk to me on the. Yeah. Hello. Hi, شباب.
Yes, doctor.
Okay, I can hear you now. Okay, very good. Okay, Hassan, you hear me well?
Yeah, very well.
Okay, very good. So, Alhamdulillah, it's back now, so it's okay. We'll start. First, I have an announcement that the department sent to us that some of you have got already the book, but some did not get the book. If those who did not request for the book, they can do this again. They can request for the book again, for the textbook again, so they can get it. Previously, they told us, the Dean Chief of Students told us that only they providing the book for the textbook for those who submitted the form requesting the book. But now they said if you did not request the book, you did not get the book, you can do this again, and then you will get it, inshallah. Is this clear?
Yes.
Okay. Shall I start? I will have 5 minutes at the end of the class to have any other communication from your side, complaints, requests, anything. But let me start now, inshallah. Okay. Let me get the laser pen, a laser pointer. Okay, this is what we ended last time. Is we had studied Rankine cycle. As we mentioned, this is a simple, ideal cycle for the thermal power plant. For the big plant, for Korea power plant, Zam power plant, this is a real plant. And then we discussed that, and we had an example on Rankine cycle. And then we discussed in our previous class how can we improve, what are the directions to improve the power and efficiency and the quality. And this is one of them here, which we have in the last one. Okay, this is ideal Rankine cycle with superheat. As we have seen, this is the original cycle. This is the ideal cycle, and what we are going to do here is to superheat that. Superheat this means that we are adding heat in this direction. Adding heat means that we are increasing the power. So this is the increase of the power, but however the heat added has been also increased, which is this area under the 4,4,2,1. So this is the area for the heat has increased, and also we have increased the work. But we have mentioned what happens to the efficiency. As we mentioned, the TH has increased, and this gives us an indication that heat is at high temperature, and therefore the efficiency will be improved. So now we have improved the power, we have improved the efficiency, and then also have improved the quality. So this is a good thing here, we can do that. But however, we cannot continue here. There's a limit here. The material engineer tells me here, you cannot exceed a certain temperature, which is about 500, 600 degrees centigrade. So the question now, how can we get these advantages and avoid this constraint? As I mentioned earlier, please stop me at any time and ask. Okay. So now what we are going to do is to introduce now a cycle which will get increase of the to superheating, and then give us more power, give us higher quality, better quality, then giving us better efficiency, but avoiding this limit here of that. Okay, so the thing here, this is what we call here the ideal reheat cycle. What is the ideal reheat cycle? So the ideal reheat cycle is this here. We are going to do, let me just to go here. Okay, this is the reheat cycle is another Rankine cycle modification. This is the first modification we are going to do in the cycle, which is real in the power plants. We have this reheat in almost all power plants all over the world. We have this reheat addition or reheat modification to the Rankine cycle. So this is here the Rankine cycle. The objective is to increase thermal efficiency and then also avoid low quality and also avoid the high temps. So what we are going to do is this. Now this is the original cycle. 1, 4, prime, 5, 6. This is the original cycle. What we are going to do now? We are going to expand this, but not all to the limit to 4 prime or the turbine, but up to a certain point here. Then we start reheating again and then doing this process. So in this case, what we have done is that we have already increased the power here, and then we have already avoided. I can go, of course, I can go this way, but the material engineer will tell me no. So I have to obey for the material engineer. I have to listen to him and then stop at this point. I cannot increase more. Then we pass it to a turbine, first turbine. Then we reheat it again in another turbine and then do this expansion. So now we did not pass this limit here. Okay, but we have already increased the power, improved the quality, and I will talk about the efficiency a little bit later. So now let us look at this diagram here. This is what we have done. Okay, so this is the boiler. It goes out of the boiler. Previously, it goes to the turbine. Forget about this part here. Forget about 2 to 3. Now it goes to the turbine and then to the condenser, to the pump, and the boiler again. This is the original cycle. All right, this is the original cycle, which is the simple Rankine cycle. We are going to modify this cycle to what we call reheat cycle. What we do in the reheat? In the reheat cycle, it goes to first here one turbine, and then I take the output of this turbine, pass it again to the boiler, heat it, and this is why we call it reheat, and then go to another turbine here. So we have divided the turbine. We have used both two turbines now instead of one. One turbine, which will have out of the boiler, it goes to at exit of the turbine to the turbine, exit the turbine, but then it is reheated again in the boiler before it goes to the second turbine, then to the condenser. So this is a modification here. We added point 2 and 3 where we take from the first turbine, pass it to the boiler, and then return it back, which is this here. So 1 to 2, this is similar to what we have before. But then this is at the middle of the expansion here. Then at this point, I take the water or the steam and then reheat it again from 2 to 3. It's reheated and then expanded in the turbine again. Okay. The first responsibility of your understanding of every cycle here is to know what is the objective and why we are doing this. You understand this diagram, and then you can produce this diagram. So in our exams, we'll most likely will give you this diagram and then ask you to provide the TS diagram. So now we have with this here, we have improved the power, we have improved the quality, and I will say about the efficiency, but then we avoided the maximum temperature. We did not increase the temperature here such that the material engineering will not be angry with us. Okay, now let me just go to the point, the third point, which is the efficiency. And let me ask you here, is the efficiency improved or not?
Yes,
Shabab,
improve.
it is improved. Can you say the name? Let me, because I do not have
Uh,
the student's name. Okay, the
Hassan.
name. Always, can you please just say your name first and then all the time, huh? Yeah, who's
Oh,
that? Hassan?
yes,
Okay, Hassan. Okay, Hassan Sayati, huh? I don't know
yes.
if you have any other Hassan. By the way, now did you get Okay, let us make it later on, which is the office hour. Okay, Hassan, why do you say it's increased? Okay, this is will be for a bonus. If you say it or anyone else, I have two bonus. No, one bonus today, maybe one bonus next time, or at the end of the class. I'm not sure of what I'm going to cover. So Hassan will answer the question. We say that the efficiency will be improved. Hassan will say why it is improved. Yes.
Because the efficiency equal 1 minus TL over TH, and we increased TH.
Okay, did we increase TH? If I look at this diagram here, did I increase TH? Remember here, TH is what here? TH is from 6 to 1 plus from 2 to 3.
Yes.
Compare it to from 6 to 1 here.
Yeah, we
Are you,
increased TH.
are you sure it's increased?
Yes.
Remember that 2 to 3 is lower than 6 to 1.
But the summation is more than.
I don't think you can decide from this one here. Now, what I'm asking is, originally it was 6 to 1, right? Now we
Yeah.
added the heat addition here. TH is from 2 to 3. Now, when we add 2 to 3, add it to 6 to 1, does it increase this way or it is less now? I cannot say it is more, right?
Okay, we can say about the area under the curve.
No, the area under the curve also, this is the heat added before. Now we added this amount of heat here. So we added heat addition, we added work, so we cannot decide work over QH. So this can be considered only half a bonus, Hassan. Anyone else
Okay.
want to explain? I know it's difficult a little bit, particularly with this diagram is given here.
Because the quality increased.
The quality increase, this is an advantage, but I'm saying why the efficiency increase? Efficiency means what? Means that we have
We
improved the
add
power
heat.
here with this amount, this box here. This box here, this is the power increase. But again, this box here up to the bottom here, this is the heat addition. So increase W over Q. W increased and Q increased. So
Faisal.
I cannot decide that efficiency is improved. Hassan goes to the temperature here. He says that the average now 6 to 1 plus 2 to 3 is better than 6 to 1. It's more than 6 to 1. I cannot decide this here. All right. And the previous one, let me go to the previous case here. Last time. Yes, for this one here, I'm definitely sure that 4 to 1 prime, the average of 4 to 1 prime is definitely more than 4 to 1. You agree with me, Hassan? This is
Yes.
very clear. 4 to
Yes.
1 dash is higher than the average of temperature from 4 to 1. But now here, I cannot guarantee for that. Anyone else want to
Yes,
The,
get
doctor,
a,
I have.
get the half bonus? Okay.
Yeah.
because we add heat at higher temperature, the reversibility less.
This is very good. This is very good. I'm happy with that because you answered related to the irreversibility there. But here again here, that this temperature, as I see it in this diagram, is lower than this one. So with this part, we add it here. I like this. Who's saying this reversibility?
Faisal thing.
Faisal. Okay, Faisal. Can you remember this when I go to the next cycle, which is regenerative cycle? Then you can get a full bonus in that, inshallah. But in this site here, I don't think so. Let me go to this here. Okay, now let us say
Yes,
that I'm
doctor.
going to heat this up to this point. So 2, 3, I'm going to move 3 here up to this point. Still, I agree with the material engineer. So instead of 2 to 3, I'm going to increase this to this point here. So at this point here, then this is the expansion at this point. Now I'm saying that if I repeat the reheat, suppose now we have infinite number of reheats. Let us see the pointer now. So let us say reheat, say expansion, reheat, expansion, reheat, expansion, reheat. At infinite time, this process will be constant temperature. Okay, Shabab, now suppose I'm going to make multiple of reheat, not only one reheat. This is one reheat. Okay, if I make multiple reheat, infinite number of reheats. So this will be expansion, reheat, expansion, reheat, expansion, reheat, expansion, reheat. First of all, do you understand what I wanted to say here?
Yes.
multiple reheat, infinite number of reheats. At the end of this interval multiple reheats, then you will find here that this is becoming constant temperature. Okay, if I make multiple reheat, multiple reheat, then infinite number of reheats means that the expansion is very small, the rate is very small. So as if I'm going here at constant temperature. Constant temperature heat addition reminds me of the Carnot cycle. Then this would be improved. So if T3 is the same as T1, then I'll go with Hassan. Yes, it will increase the efficiency. But if T is not the same as 1, I cannot decide. So in this diagram right now, I cannot decide that the efficiency is improved. But if I make the T3 as the same as the T1, then I'm definitely sure that this will give us higher efficiency, because this will be approximately constant temperature. Constant temperature reminds us with the Carnot cycle that heat addition at constant temperature, this is Carnot cycle. So let me just say something in Arabic, but don't take me for religion or anything. But I know that whatever I'm away from Quran or any discussion of that, but says that ما كان قليله مسكر فكثيره haram. ما كان كثيره مسكر فقليله haram, right?
Yes.
Okay, do you understand that? Okay, this is what I'm saying here. That this is here, if we make infinite number, this is كثيره مسكر here. So this is here expansion, heat, expansion, reheat, expansion, reheat. This is will give us Carnot cycle. And therefore, we say that this is very useful here, very efficient. Okay, and therefore, if I make only one reheat but reaching the same temperature, this is the Qalilu here, means that this is will be improving the efficiency. Okay, so this is what I'm saying here, that when we have infinite number of reheat, if I go to the limit here, then this will make it seems that I'm adding heat at constant temperature. So adding heat at constant temperature is a Carnot cycle. Therefore, definitely the efficiency will improve. Therefore, if this T3 is equal close to T1, then the efficiency will be improved. But if T3 is away from T1, I cannot decide, as a matter of fact. But let me say here, what is the objective of reheat cycle? The objective of reheat cycle is to improve the power, not the efficiency. Next time, we are going to consider one regenerative cycle, which will definitely improve the efficiency. And therefore, we will add both of them such that we have the efficiency improved and the power improved. But so let me say that the reheat cycle now, the objective is to improve the power, nothing more than that. But if it happens that 3 is close to 1, then you also have improved the efficiency. But this is not always controlled in the plant. And this is why we say we definitely improve the power, but we are not sure about the efficiency. But if you can get 3 close to 1, then you have also improved the efficiency. So this is the advantage of this cycle. We have improved the quality, we have improved the power, and also the efficiency may be improved if we have 3 is equal to 1. Okay, so this is the first thing you should understand from that. What is the objective of the cycle? How does the cycle works? And how to plot the TS diagram. So this is your first responsibility of this class today. I understand that. Shall we go to the analysis?
Yes, doctor.
Okay. So now this is the first thing you learn. What's the objective? How does the cycle work? What is the modification we have made from the simple cycle? And how to prove, how to draw the TS diagram. Then we will go now to the analysis. So it's just giving us here that X4 is improved. That's what I have here. So this is the animation. And let us now see here what are the processes as we have done. Okay, so now the processes works process 1 to 2. In this series, steam expands through the high pressure turbine stage from 1 to 2. This is what we call high pressure turbine. Why high pressure turbine? Because this is at a high pressure, as we have seen from this diagram here. This is the first turbine. This is at a high pressure. The second turbine is at a lower pressure. This is here higher pressure from 1 to 2, and this is here from 3 to 4. This is a lower pressure. So we call this here is a high pressure turbine. Then we'll go here, and then from 2 to 3, then we take this steam From the first turbine, we reheat it again. Steam is reheated in the steam generator. The boiler, we call it steam generator, which is the same name. It generates steam. Then process 3 to 4. This process is from 3 to 4. We take it back to another turbine here, and therefore this is expanded in the second turbine, then goes to the condenser pump, completes the cycle again. So this is here. We need to compute the thermal efficiency. So understand the cycle now. We want to go to the how to calculate the efficiency and the power. Okay. Remember here that when you calculate the heat, remember here you are making two processes here. From 6 to 1, this is heating. So this is heat addition. Also from 2 to 3, this is a heat addition. And I want to warn you now that remember here, some students forget 2 to 3. In this here, when I calculate QH, it is from 6 to 1 plus 2 to 3. Remember that. 6 to 1 plus 2 to 3. This is the heat addition. Why? Because we have control volume for the steam generator, the boiler. And then you see here, exit minus inlet. This is one part. Plus exit minus inlet. This is another part. So you have to consider both of them. Please remember that the heat addition is two parts, not only one part. H1 minus H6 plus H3 minus H2. Now, when we go to the turbine, the power, where is the power here? I have 1 to 2. This is expansion in the first turbine, and then 3 to 4. So now it will be H1 minus H2 plus H3 minus H4. For the condenser, it is the same as we have before. There is no change in that here. So this will stay the same. All right. So this is the analysis for that. So now we say here that eta efficiency is W turbine for the high pressure turbine, and then plus the second turbine, low pressure turbine. Then we subtract the pump, and then this is the net power out. Okay. Can anyone translate this to enthalpies? What is the enthalpy here?
Yes, doctor.
Yes, can you say it? What is the enthalpy for this part?
It is H1 minus H2.
Very good. So this is H1 minus H2. Forget
Plus
about the mass flow rates now. Then plus this one.
H3 minus H4.
Very good. Excellent. Then minus W pump. What's W pump?
H6 minus H5.
Very good. So now Hassan, I believe.
Yes, Hassan
Okay,
Sehati.
okay, Hassan here made this here. W pump, we put the minus here. So W pump will be the absolute value, 6 minus 5. Don't put 5 minus 6. So now we are saying here, this is W turbine plus turbine lower pressure minus the amount of W pump. And therefore, Hassan says 6 minus 5. This is correct. So now we take the magnitude here. Don't put another minus, so this will be added. So this is the net power. So if I want to calculate the net power, as I mentioned earlier, do not use MO dot. Make it as Hassan mentioned now, H1 minus H2 plus H3 minus H4 minus H6 minus H5. This will give you here is the power per unit mass or kilojoule per kilogram. Then if I ask you calculate the net power, after you calculate, then multiply the amounts here in enthalpies by M dot. This will give you the net power. Okay, can another one say what's this is the heat addition here. What's Q6 to 1? Another person? Say name.
Yes, Doctor.
Go ahead.
H1 minus H6.
H1 minus H6.
Yes.
H1 minus H6. So this is the heat addition in the boiler. Very good. Excellent. Plus
H3 minus H2.
H3 minus H2, which is the reheat here. Okay, so this is here the heat addition in the boiler, and please, I'm saying now that if in the next exam, 2 students in this class will forget this part. Do you challenge me? I'm saying the next exam, not in the previous exam. In the next exam, 2 students will forget that. So please do not be one of those. Okay, because this is a reheat here. Okay, so this is regarding the efficiency of the reheat cycle. And this is, I think, all what I want to say here about the. Let me just give me a minute to take the attendance so that I don't forget that, and then I'll come back. I'm not ending the class. I'm just taking the attendance in the middle here. Sometimes I forget to take that. Okay, where is this here? On the other one. Okay. Okay, we can make it also in the other class and the other. Okay, now I get that. Now we return it back. Is everything's okay? Shabab?
Yes.
Okay,
Yes.
Yes, yes.
very good. So now any questions regarding what's the objective of the heat cycle? What are the modifications for the cycle? And how does the cycle work? And your responsibility is to plot the TS diagram. This will be almost part of each question, plot the TS diagram. And then how do you calculate the power in kilojoule per kilogram, and then how do you calculate this in megawatt, and then how do you calculate Q dot H, and then how do you calculate the efficiency. This is the most important parts here, and the problem will be like that, nothing more than that. We give you a problem, we just give you the pressure, temperatures, and everything here, or if I make it easier for you, I give you the ensembles, such that I avoid problems from thermodynamics 1. So I give you a problem like that. I may give you the diagram, but you should know it now, and you should know how to plot this diagram, but most likely we give you the diagram. Then I ask you part A, plot the TS diagram. Part B, calculate the power in kilojoule per kilogram, which is said delta H is here. Then I ask you calculate the heat addition per kilogram. Then calculate the efficiency. Then calculate the net power. So multiply by the mass rate. Calculate the rate of heat addition. Do that. That's it. No more than that. So this is a question. It's a problem we get in a quiz, in an exam. We do not want to complicate anything, but this is just to understand what is the cycle here. Okay, just to go and give you some complications again here. This is okay. This is the modification we have done, and this is what, remember this diagram all the time. We want to go to this one. This is the real plant. So what did we do now? You see here. This is a boiler here. You see out of the boiler here, this is the superheater. You see this one? This is a superheater. And then it goes here to the first turbine. This is what we call high pressure turbine. Then where is the output from that? This is the output. It goes back again to a reheater. And this is the reheater goes here to a turbine here. More, we will have more than one turbine. We'll say this later when I take the regenerative cycle. But I want you to relate what we learn in the class and what you have in the field. This is what you have in the field. This is the boiler here. This is the superheater. You see the superheater here goes from the superheater, which is state 1 in the previous slide. Let me just go to again here. This is slide 1. This is a boiler here, and this is what we call, get it from superheater here. This goes to state 1. State 1 here is this point here. So this is state 1. It goes to the high pressure turbine. Out of the turbine, high pressure turbine is state 2. Then this is state 2 goes to a reheater, then gets out at state 3. It goes to the next turbine here. But here we have high pressure turbine, intermediate pressure turbine, low pressure turbine. So just let us understand here. I want you to relate what we have in the class, this side, to what we have in the plant. All right? You are on Korea power plant now. Okay, so we are engineers. We have to understand we are not just taking a cycle and so on, but we are presenting a real diagram, a real plant in our class here. All right, Shabab? Simulation is okay. Shabab. Hello?
Yes. Yes. Yes.
Okay.
Yes.
Okay,
Yes,
just
yes,
be with. Yeah, I don't want to lose you, so sometimes I cannot hear you. I remember we were taking after getting my PhD, and then we used to take some lectures on how to class and so on. So I was in Egypt at this time. After I left from London, I got my PhD from Imperial College, and then I went to Egypt for a couple of years. before I go back to USA. So then what happened is that one was explaining to us a certain story, yeah. And he said that he was working in Saudi Arabia here, and he was teaching to ladies, female students. And in this here they have, I think, some walls or something like that that he cannot see the students, but the student can see him. And in the middle of the class, one student, one female student left and told him that, dear professor, I'm going to leave now, and I'm the last one to leave. Everybody has left, and then I am going to leave now, so nobody's here. And he told us, what should I do now? Should I continue my class, or I have to stop here? So this is just what I'm. So this is why I want to hear from you that you are still in the class. Did you get my point from this story, or?
Yes,
Yeah, I
yes.
just
Yes.
want to get, sometimes I want to get your attention. If
Great.
one is sleeping or something, then he will wake up again. Okay. Right. So this is here what I want. This is why I ask you every while, are you still with us? Okay. So now I want to keep your eye on the class and look at the field here, such that we are explaining the field. We are simplifying what you have in the field. So instead of giving you all of this here, superheater, reheater, but this is the actual thing. It's just the tubes like that here, and these tubes, and then go to the hyper. But I think you can relate this now. It is the same as we have, but we are just simplifying the picture from the real plant. All the time I will go to this whenever we need, such that at the end I go back to this and make sure that you really understand it. So when you go to Korea or Ghazlan, can be experts. So when you go there, they will not tell you that you are a fresh engineer. They tell you, yes, you are an expert in steam power plants. Okay. So now we got here. This is another part here. This is a supercritical ideal reheat cycle. Okay, supercritical ideal reheat cycle. In this case here, we have high pressure at this point. This is supercritical, and therefore we have the pressure. We have this is the thing. So it does not pass through the saturation region. Remember that we used to have this and then go to the saturation region, then go up. So only the difference here is that you have a high pressure such that you do not go to this point. So this is here is what we call supercritical ideal heat cycle. It's not much used. We do not have this in Ghazlan or Korea, but somewhere in the world they use that, and this will give you more power. But of course, it needs more precautions here because of the tubes that you have to have. There'll be higher stresses on the tubes and so on. Okay, so now what to say here, so you can go to thermal, you can achieve 47%. In real plants we go to 42 or something. So now if you put this recently here, then you can go to 50% with supercritical pressure. So it is the same as the previous one. The only thing here that this pressure here is high pressure, such that this does not pass through the saturation region. All right. Now we took all the previous cycles. We considered what we call the ideal cycle. So let me just go back here and say what do we mean by ideal cycle. This is ideal cycle means so many things. One thing is that you consider this isentropic, and this is what we have studied so far. Is this is isentropic. So now we are at the beginning. We considered ideal simple cycle. With the reheat, we moved a little bit away from being simple cycle. We complicated a little bit by adding the reheat. We are going to make another modification later on, but now we are going to stop a little bit from the modification and go back to ideal. So far, we are studying ideal. If this is ideal cycle, of course, this does not happen in practice. In real case, does not happen. But what happens that this is irreversible, and therefore entropy will increase, and therefore it goes a figure, something like that. Also, the pump. The pump is always, this is also isentropic. So this is what we call ideal. In real cases, there's nothing called isentropic, so this will also have a process like that, 5 to 6 actual. So this will be the inlet to the boiler. So these are the two main things which are the irreversibilities that we have in the cycle. Now today we are going to move from ideal cycle to real cycle by adding the irreversibility. So this is what I'm going to talk here. Irreversibilities are associated with each of the subsystems. Every system of these, it has irreversibilities. And therefore, the principle, the reversibility will take you out from being ideal, and therefore we have irreversibility in the boiler, we have irreversibility in the turbine. In each part of this, we have irreversibilities, and therefore we are going to consider these irreversibilities in this class. We are going to concentrate more on the major parts. There's some other irreversibilities. I don't want to uh, 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 cause problems for you to such that to go more into irreversibility, but I consider the main parts. Okay, so irreversibilities, let me go here. The main irreversibilities will go here into the turbine and the pump. And I will concentrate more on the turbine, not on the pump. Can anyone answer me? The okay, we have irreversibility in all of that, but the major one is in the turbine and in the pump. But I can say here that the turbine is most important than the pump.
because
If
it
I neglect
produce
this
much,
part, this will be okay. Why?
because it's produce a lot of power, and the pump take small amount of power.
Okay, very good. This is what last time I had. Who was helping me in that? I think Faisal or I asked two of you
Yes,
to remember that the turbine power is much more than the pump, or the pump is very negligible for
Y-
the turbine. So if I have
yes.
irreversibilities here, if the total amount is 6 kilojoule per kilogram, then irreversibility will make it 7. So what's heck of that? What's the problem with that? But here, if I have 1,000 and this will be 700, this is a major loss. So here in all the time, if this is a compressor, yes, I cannot neglect that. But because it is a pump here, the pump itself work is negligible, and therefore I do not take care much about that. Okay, so now we are going to consider this here. And I'm sure that you know this from thermodynamics 1. So remember here that in the previous example we calculated, we took S2S is the same as S1, and then we got the enthalpy. But this is not real. When you go to the plant, 2S is not there. If you measure the exit of the turbine, it will be 2, not 2S. So 2S in your office or in the class here. So when you are in your office, you can have 2S. But when you go out, talk to the technicians and engineers, you see only 2. All right, so the exit of the turbine is 2. Don't go out to the technician, tell him 2S. He will know that you are just a fresh engineer, you just graduated, and then you do not have an experience. So 2S in your office only. Why 2S here? Because 2S is the only way to get you to 2. So if I need to get 2, then I have to go to 2S. Then I go to 2. It's like the angle here. Go vertical and then shift an angle to get 2. So 2S is to help us at 2. But after I do that, I don't want to say when I calculate the power, don't say H1 minus 2 H2S. This is wrong. H1 minus H2. So when you measure the pressure on the X at the exit of the turbine, it is 2, not 2S, right? So when you are in the field as an engineer, I don't want to say 2S at all. It is 1 to 2. But 2S to help you to get 2. So now what we do say the efficiency is W turbine. This is the actual turbine over the isentropic value. So this is you calculate the isentropic first, and then from this eta turbine you get H1 minus H2, and when you calculate the power, it is H1 minus H2. Nothing about H2S again. Okay, so this is here is well. So what would be the problem look like? The problem will look like that. I'll give you state 1, the pressure 1, and T1, or I say it is saturated, whatever. So I give you the proper pressure and temperature here, and I give you the pressure here. Then what you do here is to go from 1, get H2S. Then you apply this equation and then get H1 minus H2, or get H2 to use it in your calculations. So this is the way to do it. In practice, in actual cases, what do we give you here? What's given in a problem? Is it eta turbine normally given, or what? So now I have eta turbine and H2. Either I give you H2 or I give you eta turbine. So if I either define state 2, then you can get eta turbine. Or I give you eta turbine, you can get H2. Okay, let me say this. At the beginning, when you buy the equipment in the design stage, in the specifications of the turbine, you will be given that. All right. So in this case, you have this value, and accordingly, you go and get H1 minus H2. But later on, after 5 years of running the turbine, then you have some deterioration here. So 2 may be a little bit to the right here because of more irreversibilities and so on. So what you need to do is to evaluate the turbine. So you go to the plant and measure the properties at state 2 and then get H2. Then you evaluate eta turbine and see how much eta turbine is less than the design value. And therefore you can do some modification. Am I clear here, Shabab?
Yes.
Okay, so
Yes.
Yes.
most of the time in our problems, eta turbine will be given. And I'm sure that you know how to do that here. Okay, if you understand this well, I will ask you, how about the pump? Anyone can tell me, write this equation, say, read this equation again for the pump. Eta pump, if this is a pump now, eta pump will be equal to what? What
H
should I put here?
H2S minus H1 over H2
No,
minus
no,
H1.
talk about the pump. This is the pump here. 3 to 4,
Pump
not 1
H4
to 2.
minus.
Ah,
H4S minus H3 over H4 minus H3.
excellent, excellent, very good. So you put here the isentropic in the upper part, and then the actual. You put the heater turbine, the isentropic above here, and the actual is here, opposite than the turbine. Okay, so just reverse the values here. So now eta turbine 1 over minus 2 over 1 minus 2s. Eta pump is 4s over 3 over 4 minus 3. Okay. So this is what we have. As I mentioned here, these are the two main irreversibilities that we are going to have in our problems, in our discussion, because this is real. Other irreversibilities are small, but then even that one here, this will be, as I mentioned, also all of this is neglected, and therefore the change from here to there is always neglected. So it is also a small here. All right. So here is this is the actual work, just giving more explanation as I was saying here, and this is so this is here is referring that this is the actual here. This is 1 to 2 is the actual value, and then we have this is the isentropic value here, and also it's referring to that. I think the slide is clear even without my talk here. Okay. Also, you go to the online course and you can learn from that. Okay. So this is what I have here. This is what you already answered. You answered me that eta pump is 4s of minus H3, and this is 4 minus. If you reverse this, eta will be more than 100%, and this is what's it's not acceptable for us. All right. So this is here what I have. There's also explaining this to you here. Okay. So this is here is what you do in that. Okay. Um, okay. This is the next part here that we are going to make another modification. Let me just in 1 minute, I'll just say about this here. This is the next modification we are going to do. So this is what I'm going to explain in our next class. Sometimes I ask the students, can you please read the next lecture before you come to the class? It seems I'm dreaming. This is the exergy here. Okay, can I ask you to read the next lecture before you come to the class? Just try to understand a little bit, and therefore you will be ready to discuss more than than if you do not read that. So this I'll stop at this point, and this we are going to consider in our next class. But now I want you to go read an example from the book in the reheat cycle and try to solve it and so on. All right. Any question first? I'll give you 1 or 2 minutes to have any question in the lecture today. Then after that, we'll go and talk about other things. Since there's no question in the class, any other discussions? One comment I mentioned at the beginning of the class that if you do not get your book, then make sure that you fill a form sent to you or to request the book. If you did not request the book last time, then do it again. They allow you now to do this again, but quickly, please, because this will be ending next week. Okay. Any other complaints?
Where's
دكتور
this form?
I'm sorry.
Where's this form you're talking about?
I think they send it to you. Can anyone who filled this form can explain? Because I'm not aware of that. How did you get the form يا شباب؟ الناس اللي أخذ الكتاب.
هما أرسلوا الفورم أول يعني وقفلوه.
أرسلوها في إيه بإيميل ولا؟
ايه
أيوه.
بالايميل قبل اسبوعين.
طيب can you the one who's asking can you ask this mail or can any one of you send a form by email to him? Put it in WhatsApp. I mean try to help يعني because I cannot do that. If you do not have it and the students cannot give it to you now or send you or you see your email back so you may have get it
دكتور
then you send it to the Deanship of Student Affairs. Yes please.
the form is for what دكتور؟
The form is to get the book. I remember they told us here that they send a form the students to fill them that they request to get the book, the textbook. If some students filled that and they got the book, they were saying that they will not get the book to the other students who did not fill the form. But the department asked them and they agreed that if you do not have the book, you do not fill the form, please do it now. Fill the form and a request for the book. I don't know how the process of this process, but on the WhatsApp you can help each other. Or you can send the department, you can send to the Deanship of Student Affairs, but you have to send this form to get the book.
So
Okay,
the form is open again. So
the form
it
is
closed
open again.
last time and it's open again.
How can he get it? I don't know, but I don't know how it did reach you because I'm not in the process. But
Okay,
it is
خلاص.
open again.
طيب
It is
ماشي.
open. Did we give any help to the student to ask? Let me go to the teams so I can see the names here. Okay, شباب, someone asked that where is this form? I mean, how can he request it again? He did not request the previous time. Can you help him or not? Tell him where he can find this form or this open or whatever. Yeah. How did you get it or someone sent by email? Okay, so can you provide help to him either on WhatsApp or see what. Okay, type. Thank you much. Another thing, I'm preparing for the next exam. It will be at the end of this chapter, and I'm trying to make it as you discussed last time. You advised that you want to have 2 exams instead of 1 exam. Okay, so I'm trying to do this. So I'll give you 2 exams. I mean, 20 minutes in one class and 20 minutes in another class. And of course, the minimum is 5 and the maximum is 10. So if this is the case, so each one will be allowing 5 points or 4 points, something like that here. But will be 2 exams. If you like this or 1 class, it's up to you. I can do either one of them. So this time I will make some modifications a little bit. So I'll give 2 problems. One problems for someone who have their 7th digit is even or their 7th digit is odd. So I'm going to divide you into 2 groups. It will be the same problem, but the data will be different. So whoever have his 7th ID, for example, and it depends on what in the exam, is even, then he will solve a problem. If he has his 7th digit is odd, then he will solve another problem. Also, I'll put some, for example, the mass flow rate will be A plus B, where A is the 5th digit, B is the 6th digit, and so on. And part of the question will be calculate this and tell me what is the data, which problem you are going to choose. So, and this will have 2 to 3 points. So I don't want to, it's not difficult to get this, I believe. I mean, add the 6th digit to 7th digit. So, but write it. This will have some points to do this, only this. Huh? Okay. So what do you prefer? I make it 2 quizzes or 1 quiz? يا شباب.
Maybe Dr. One long quiz is better.
طب can you Hassan discuss this and say what's the majority will be better? One quiz for around 8 points or 10 points, or two parts will be on two classes, 20 minutes and 20. I prefer myself one quiz, one full class, and that's better for me. And there's, this will not disturb my class, but it's up to you. So Hassan, can you make I mean, get the answers for the students and see what they prefer. Yeah. Okay, but let me know today about the office hour, please.
Okay,
Okay.
inshallah.
Okay. Thank you much, Shabab. Thank you, Jazakumullah khair. Thank you. See you on Saturday, inshallah.